All right, we're going to work on some practice problems with this material that we've just looked at. So a minimization problem example. Given this subspace, M is the span of these two vectors. Notice they're independent of one another. This vector is not a multiple of that, nor vice versa. And we wish to find the M star in this subspace that is closest to this vector. We can see that this vector is not in this subspace because everything in this subspace has 0 as a second element. Okay, this does not have 0 as a second element. All right, so we now decompose y into two vectors, y1, which has the 0 in the middle, and y2, which is the stuff that has, which is non-zero in the middle and 0 everywhere else. Okay, so we can see easily that these two vectors are orthogonal to one another. Just take this transpose times this, you'll get 0. Also, if you take this vector transpose times either of these two vectors, you'll also get 0. So we have that this is in M. So you can go through and show that this vector is a linear combination of these two vectors. So this vector is in this subspace, and y2 is in the orthogonal complement of this subspace. Okay, and so M star then is the projection onto this subspace, which we didn't even come up with a projector for this problem. Didn't have to. In this case, it was easy enough to see what the projection was going to be. It was just the one that made that middle term 0. The error, which is y minus M star, is y2. And we see that that is in the orthogonal, it's orthogonal to M, which is what we had proved earlier, and now we can actually see it here. So this is an example. Let's move on to a little different example. Here I have a 3 by 2 matrix. Okay, this matrix actually maps vectors in 2D into 3D. So it does what's called a dilation. It expands the space from 2 dimensions to 3 dimensions. But notice that the third dimension will always have a 0 component in that third dimension. Suppose now that y has a component in the third dimension, for example, like this. All right. So we take this matrix and we choose the subspace to be the range of that matrix, and based on that we have this projector. So we can go through and establish how that is obtained. We'll talk about that in a little bit. And again, we can verify that the range of E is equal to the range of A, which is in fact the definition for M. We can go through and show that E squared is equal to E, and it's self-adjoint. We can also show that E times A is equal to A. So all of these can be shown. Therefore, M star, which is E times Y, so E times Y, basically zeroes out that third component, which makes sense because our subspace had always had zeros in that component. So again, this is a similar example. Here we actually show the projection, or the projector. So in this case, the projector was pretty easy to see because of the way A was defined. A is basically an identity in zeros, and so the projector is a square matrix that has the same identity and then a 0. So what happens if it's not so simple? Let's look at an example like this. So here M is the span of these two vectors. And so we define F to be the matrix formed from those two vectors. We then plug that into this formula. E is equal to F times F transpose F quantity inverse times F transpose. This is the projector. When we go through and plug this F in, we get this matrix. Okay? It may not be obvious, but you can go through and show that in fact E, well, you can see that it's symmetric, right? That the off-diagonal elements are symmetric, and it's symmetric, and you can go through and show that if you multiply E by itself, you get itself back. Okay, and so this would be the projector then onto that subspace for this particular problem. So given now this subspace, which we looked at before, we wish to find M star in M that is closest to Y, which we've seen. So how do we find Y1 how would we find y1 and m? So before we kind of, you can intuit what y1 must have been, right? So we saw that y1 was 1, 0, and 3, and it just intuitively was that. So otherwise, we can go through the formality of using the projector. So again, m is this span. So again, we take the columns and form them into a matrix. And again, we plug that into the formula, and we get this projection, this projector, which kind of makes sense. We have a 1 here, we have a 1 here, and then a 0 in the middle, just like you might expect. Well, you might or might not expect. Okay, so the optimal then is the projector times y, which again zeroes out that middle element, which is indeed y1. So we saw intuitively this was what y1 must be, what the optimal must be, but now we've actually gone through and shown that when you actually do the projection, you get exactly what you expected. So our guess, or my guess, was accurate. We talked about curve fitting. So suppose we have some data like this, and we want to find a line that best fits this data. Okay, so how would we go through and work with this? Well, we saw that if we defined the matrix X to be the values of X and then all ones, and let Y be the values of Y, P, which is the pseudo-inverse of X times Y, comes out to be this, which basically says that this first element is M, the second element is B. So we have the slope and the intercept for this data. And if we were to plot this, we would see how the curve fits. We can see that not all the data are on the line. Not all the data are on the line, and therefore Y is not in the range of X. Okay, so where we're talking about this X, Y is not in the range of X. This is an example where Y is not in the range of, if it were in the range of X, it would pass through every data point, but it does not pass through every data point. Okay, suppose now we're given this data, and we again want to find the line that best fits the data. You have these slides, so you can check this data out for yourself. So we go through and we do the curve fit, and this is the slope we get, this is the intercept. When we plot the slope and intercept versus the data, we can see that the fit is not that great. This is the example that I showed earlier, where we have the data looks far too curvy to fit this line. There's too much of a pattern here. So we go through and we try a quadratic curve fit. So here, when we do that, these are the values of A0, A1, and A2, and we can see that when we fit the data, it fits a lot better. This data fits a lot better than the line fits. Okay, so then this is a better fit for the data. So you're probably asking yourself, well, what does the MATLAB code look like that does this? So this is the MATLAB code that does this. I've set up my X and Y values. And to do the nonlinear curve fitting, MATLAB actually has a function called polyfit. Polyfit will do, so this does polyfit of order 1, so that's a linear function. Order 2 is a quadratic function. So polynomial 1, polynomial 2. So this is the one that has the slope and intercept. This is the one that has the quadratic coefficients. Then I can use this function polyval to evaluate the polynomial at the values of X that we're working with. And then here I've actually gone through and done the plotting and so forth. So this is the code that can be used to do that. So practice problems. We're getting some practice with MATLAB here as well.